Hi everyone. So in this video, I'm going to go over some of the questions that you all requested from the midterm review. I'm not going to go over every single question that was requested because there were a lot, but I'm going to go over basically the ones that were requested by more than one person, as well as a few others that I thought were especially good to go over. So I will put in the description for this video a list of all the questions I go over. And then a timestamp so that you can jump around if you only want to look at a few of them and you don't want to watch the whole video. So first question that was requested was, we're going to look at numbers 1A and B. So let me go back to other page and write those ones down. So for 1A, we have the limit as x approaches 0 of f of x, where f of x is equal to a piecewise function. So basically what's going on for a piecewise function is that, so for a lot of the other problems in this section, you're using different algebra, right, in order to evaluate the limits. For a piecewise function, there's kind of something extra going on, which is that you have two different functions, and if you notice, the place where these functions kind of join up is at 0, and that's the place where we're taking the limit. So you actually have to worry about whether the left and the right-hand limit agree with each other or not. That's not generally going to be the case if you're using algebraic simplifications like you can in a bunch of the other ones. You don't really need to worry about the left versus the right-hand limit. But when it's a piecewise function, because you don't just have kind of one nice function, because you have these kind of multiple pieces being glued together, you do have to check whether basically the ends meet up or not. And if they don't meet up, if there's a space in the graph, then the limit will not exist. So there's kind of two different ways to do this. You could totally do this just by looking at the equation or the equations. So if you wanted to do this by looking at the equations, you could use the top equation. So notice that the first equation is what you use if x is less than or equal to 0. So if you're going to take the limit as x approaches from the left, you would use this. So the limit as x approaches 0 from the left, you can actually just, because this function is defined at 0, you could just plug 0 into this top equation, because this is the equation that you use when x is less than or equal to 0, so when you're on the left-hand side of 0. And then similarly, you could use this equation for the limit as x approaches 0 from the right of f of x. But personally, I actually like to draw a graph instead. I just think that it's a little bit more intuitive for what's going on. So let's just sketch a quick picture, and it doesn't need to be perfect. It's really just to kind of give yourself some intuition for like, why are you using one equation for left and one equation for the right? I think it's a lot easier to see it if you actually draw it. So what does this function look like? Well, the first part of it is supposed to be like x squared minus 1. So that's a parabola that's been shifted down by 1. So let's put some numbers here. So if it's been shifted down by 1, it would look like, and I'm going to draw kind of the full picture of the parabola first, and then we can take off what we don't need. So this would be the parabola if there was no restriction, but you're only supposed to use this equation if x is less than or equal to 0. And so that means we want to get rid of this part. And then we want to put a closed circle on this point, because when x equals 0, you use this part of the equation. And so then we can graph the second part. So the second part is a line, so 2x minus 1. So that's a line with a slope of 2 and a y-intercept of -1. So that means that we're going to want to go up 2 over 1, draw our line. And then again, we realize, okay, we're only supposed to use this equation when x is greater than 0, so we can get rid of this part. And so basically what we can see here is that if we're taking the limit from the left and the limit from the right of this function, they're going to meet up at the same point. And so the overall limit is going to exist. So we can say the limit as x approaches 0 from the left of this function is equal to, so looking at this picture, it's -1, right? So we're looking at as we get closer to 0, as we're kind of zooming in on this point, what is the y coordinate getting closer to? It's getting closer to -1. And then the limit as x approaches 0 from the right also equals -1, because if we're going in towards 0 as an x coordinate and we're seeing where's the y coordinate heading, it's heading towards -1. And that's the same thing you would get if you were plugging in, if you just plugged in 0 into the top and bottom equation, then you would get the same result. And so because these two agree, so anytime the left and the right-hand limit agree, you can conclude that the overall limit is equal to whatever you got for the left and right-hand limits. Okay, so let's look at B, which is a very similar question. So B is asking us to find the limit as x approaches 0 of g of x, where g of x is equal to another piecewise function, but this time it's x squared if x is less than or equal to 0, and it is 2x minus 1 if x is greater than 0. So it's going to look a lot like our last one, right? Except for the only difference is that now the parabola part is going to just be a parabola that is has its vertex at 0, 0. So for the first part of the equation, or the first part of the function, we can graph a parabola that has its vertex at 0, 0. And then we only want the negative half, right? Because we're looking at x is less than or equal to 0. We put a closed circle there because you use that equation when x is equal to 0. And then the next part is 2x minus 1. So that's like the last one we did. That is a line with a slope of 2. And then, I'm not going to even draw that second part because we already know we don't need that part. And then we would put an open circle on this one because when x is equal to 0, you don't use this green part, you use the blue part. And that's what that open and closed circle kind of represents. So in this case, if we're taking the limit as x approaches 0 from the left, we would get 0, right? Because if you're kind of zooming in on this point from the left, and you're seeing what is your y value getting closer and closer to, it's getting closer and closer to 0. And on the other hand, if we're coming in from the right, then like the one above, the limit as we approach 0 from the right is going to equal -1. And so anytime these left and right hand limits don't agree, that tells you that overall, if you take the limit without specifying left or right hand side, basically it does not exist. All right, so we're going to move on to let's look at, let me pull back up the requests. So we're going to look at 1E and I think probably 1G. So now this is getting into limits that you can actually evaluate using, using algebra. So 1E, actually, sorry, let's do that one. I want to go in order. Sorry, 1D was also requested by a few people. So let's actually do 1D first. So 1D is asking you to find the limit as x approaches pi of sine of x over x. So this is kind of a trick question where it's easier than it might appear. So you might look at this and think of like, oh, maybe it's the squeeze theorem or something like that. But remember that if you have a function that is defined at the number where you're trying to take the limit, you can just plug that number in. The one exception to that is with piecewise functions, right? Piecewise functions, you have to think about the left and the right-hand side. But in general, if your function is like a nice function, if it's some combination of trig functions, polynomials, rational functions, we had that like long list of all the different types of functions for which this is true. If it's that type of function, and if it's defined at the x value that you're looking at, then you can just plug that number in. So in this case, I mean, let's at least try it, right? So let's try to plug in pi. So we would get sine of pi divided by pi. And so what is sine of pi? Well, if we look at on the unit circle, if we go to an angle of pi, so pi would be like 180 degrees. So over here, this is our angle pi. And the coordinates of this point are -1, 0. So sine of an angle is always the y coordinate. So that means that sine of pi is 0, divided by pi, we get 0 as our overall answer. So remember that pi is a number, right? You might look at that and think it's a variable or something else. It's just a number. So treat it like a number. See if you can plug it in. If you can, great, then you can do that. Okay, so next one up was number 1e. So this one asks us to find the limit as x approaches -2 of x cubed minus 4x divided by x plus 2. So remember that when we're dealing with limits, and if it's not a piecewise function, so first thing you want to do is see whether you can plug the number in. So that was what happened in the previous problem, is we plugged the number in, and that was it. That was our answer. In this case, if we try to plug in -2, we'll get 0 in the denominator, and so it will be undefined. So if you can't plug the number in, then that tells you that you want to use some algebraic simplification. So in this case, because we have a polynomial and another polynomial, we want to try to factor. And I've seen some comments of people saying, they don't know when to use what rule, and it just really depends what your function looks like. So, the other methods that we have, and we'll see some examples of these a little later, we have this idea of multiplying by the conjugate. So that method only makes sense if you have square roots. If you don't have square roots involved, that wouldn't be an approach that makes sense at all. The other method that we talked about was making a common denominator. That only makes sense if you have like multiple fractions somewhere. So in this case, we only have one fraction. There's no common denominator to even make. And so the only method that makes sense in this case is factoring. So we want to try to factor the numerator and see whether we can get anything to cancel out with the denominator. So I would start by factoring out an x, right? The numerator, everything has a common factor of x. And so what are we left with inside the parentheses there? Well, that is what's called a difference of squares. So something that is of the form x squared minus 4, that's going to factor as x plus 2, x minus 2. And then we still have x plus 2. And so now we see that we have something that can cancel out here. And the reason that is good is because that was the whole issue with this limit, right? We couldn't plug in -2 because we had an issue in the denominator, but now there's no denominator left to be an issue. So we can just plug in -2, and so we get -2 times -4, and that's equal to 8. Okay, so next up we have, let's do 1g. So 1g and 1h have a very similar approach. So I'm just picking 1g, but I think if you can do 1g, and you can probably do 1h. They're very similar. So 1g is asking us to find the limit as x approaches 0 of the square root of 5 plus x minus the square root of 5 minus x, all divided by 5x. So again, first thing, see if you can plug in your number. In this case, you can't, right? If you try to plug in 0, you'd get a 0 in the denominator. That's undefined. That's a no-go. And so we need to use one of our algebraic simplification methods. So as soon as you see square roots involved, that's where you say, okay, that's this whole multiplying by the conjugate business. So we're going to multiply by the conjugate in the numerator and the denominator. So what does the conjugate look like? You're just changing the sign of the part between the two square roots. So you're not changing anything inside the square roots, you're just changing it to, instead of being a minus, it's going to be a plus. And it comes back to this idea of a difference of squares, actually, because when you multiply two things together, if they're exactly identical, except for that the only difference between them is one has a plus and one has a minus, when you multiply them together, you'll just get the first thing times the first thing, so a squared, minus the second thing times the second thing, because this plus and minus kind of cause the middle terms to cancel out. And so in this case, that plays to our advantage, because when you multiply a square root with a square root, the square root goes away. One thing to be really careful of, make sure that you do that in the denominator as well. You're not allowed, like if you just were to take this and just multiply the numerator by something, you would be changing the function. And we need to make sure that we're not really supposed to be changing the function in any fundamental way. We're just supposed to be doing kind of simplifications that kind of leave the function pretty much the same, but possibly help us get rid of an issue, like a discontinuity with the function. Okay, so what do we get here? When we multiply together the first two square roots, we get 5 plus x. And then the second part, and this is another place where students make mistakes a lot, is that we need to put parentheses around this, because you're subtracting the whole entirety of whatever your second part was. So in this case, the second part was square root of 5 minus x times square root of 5 minus x gives you 5 minus x, and then you have to subtract that entire thing. Another thing to be careful about is that you don't want to go and distribute stuff in the denominator, because generally speaking, that's going to make it harder for you to see what can be canceled out. So in the denominator, just kind of bear with it, assume that something will eventually cancel out, and just kind of leave it as is. Resist the urge to distribute anything in. Okay, so what's going to happen in the numerator? Well, we have a 5 and then we have a negative 5. So those are going to cancel out. And then we have x minus negative x. So that's going to become 2x. And then we have 5x times all this stuff. Okay, so now we see that we can get rid of this x. And that's great, because that was the x that was actually like the whole issue in this limit, because that was what would make the denominator 0 when we tried to plug in 0. And so now we're actually going to be able to plug in 0. So let's rewrite this in its new version, and we'll see that now there's going to be no issue at all with plugging in 0. Right? So if we plug in 0, we're no longer going to get 0 in the denominator. And so now we can just plug it in. So we get 2 over 5 times the square root of 5 plus 0. So that would be just 5, right? Plus the square root of 5 plus 0, or 5 minus 0, which is another square root of 5. And so this simplifies to 2 over, so these two things together are 2 root 5, right? There's 2 of them. And so now we have 10 root 5, because we have 5 times 2 root 5. And then this can be simplified to 1 over 5 root 5, right? Because the 2 and the 10 are both divisible by 2. So we're basically just dividing both those by 2. And then if you wanted to, and I'm not sure how I wrote it in the answers, I would be fine with this. But you could also rationalize the denominator. So rationalizing the denominator is when you multiply by, basically multiply by the square root. And you could actually just do root 5 in this case. So if we were to multiply this by root 5 over root 5, we would end up with square root of 5 over 25. So that would be fine as well, but I would be fine with you leaving your answer in the first form in this case. All right. So let's see what else we have. Just looking at our list here. So we're going to look at 1L and 1M. So we're now going to be kind of changing gears and looking at limits that are limits at infinity. Maybe I'll go to a new page. So these next ones are going to use a different method. So 1L and 1M are both limits at infinity. Maybe I'll just go back to this page for a second so you can look at them. So we're looking at these two. So when you have a limit at infinity, the approach is different. So with the other functions, the issue is you can't plug in the number because the function is undefined, right? That's the main issue. And so you have to do simplification until it becomes defined. For limits at infinity, where you're taking the limit as x approaches positive or negative infinity, it's no longer an issue of whether the function is defined or not. You can't plug in infinity because infinity is not a number. So there's no like simplification you can do that allows you to magically plug in infinity. That's not what's going on. What we do instead is we use this kind of method that helps us break down these functions into pieces where we do know what the limit is. So the key fact that we make use of on these, okay. So let me write down the first one. So this is 1L. So the key fact that we're going to make use of on these is that if you take the limit of a number divided by x to a power as x approaches either positive or negative infinity. So I'll write this down to the side. Key fact. If you take the limit as x approaches either positive or negative infinity of a number over x to a power, it's always going to equal 0. And that's because you'll have like a number like 5 divided by something like 1,000 or negative 1,000,000 or something like that. You're going to get these numbers that are getting smaller and tinier fractions, getting closer and closer to 0. So basically what we're going to do is we're going to go through this function and rewrite it in a way that we can make use of this fact. So how do we do that? We go through and we divide every term by the highest power of x. And specifically, not just the highest power of x in the whole thing, specifically the highest power of x that appears in the denominator. So in this case, the highest power of x is in the denominator anyway, so it doesn't really matter. But like in the next example, we'll see that would actually mess you up if you didn't divide by the highest power of x in the denominator. So in this case, our highest power of x is x cubed. So we want to go through and we're going to rewrite this limit so that instead of writing it as is, we're just going to go through and divide everything by x cubed. And that's okay because we're basically just doing the same thing to everything in the numerator and everything in the denominator. So we're not changing the function. We're just writing it a different way. So now we want to simplify this. So basically anything that can be simplified. So for example, negative x squared over x cubed, we can rewrite that as 1 over x using exponent rules. Then in the denominator we have 1, we have minus 1 over x squared, and then we have 1 over x cubed. So now the key step where we can make use of this fact that's in blue is we can go in and take the limit of each part individually. And so anything that's of this form, the limit of it is going to be 0 based on this fact that's up here. So we would end up getting, and I'm not writing out this step, but really what we're doing is we're kind of breaking this limit up and taking the limit of each part individually, which we learned that you could do like back in the first week of class or early on in the quarter. And actually now we don't need the limit anymore because we're bringing the limit inside. So we're going to end up with 0 minus 0 divided by 1 minus 0 plus 0. And what is that? That's 0 over 1, which is equal to 0. So that's our answer. And so what does this look like in the graph? This would mean that the graph eventually flattens out to a height of 0. It has a horizontal asymptote at 0. So you might remember some, facts from pre-calculus where it's like, oh, if the degree of the numerator is this, degree of the denominator is this. I will not give you full credit if you use those rules on the test. I really want to see you using this approach of dividing everything by the highest power of x, because it's kind of like it's kind of like plugging in numbers to a limit versus using the algebra. It's like, I just want to see that you've mastered this actual method rather than, it's great if you can get to your answer otherwise, I'll still give you partial credit, but I do want to see this specific skill in order for full credit. Okay, so let's do the next one, which is similar in some ways, but I think it's a little bit harder. So it's a limit as x approaches negative infinity of x to the fourth minus 3x squared plus x divided by x cubed minus x plus 2. So we're going to do that same trick where we're going to divide everything by the highest power of x that's in the denominator. So in this case, the highest power of x in the denominator is x cubed. So even though x to the fourth is a higher power, because it's not in the denominator, we're not going to use that one. And the reason for that, and maybe you've run into this problem yourself if you've tried it, is that if you divide everything by the highest power and it's not the highest power in the denominator, then you're going to end up with, in your limit, something divided by 0, which isn't really helpful because dividing by 0 is undefined. So you'll basically just kind of give yourself a new problem that you're stuck on. Okay, so all right, so now let's simplify this. So we have the limit as x approaches negative infinity of, and the first part is x, second part is minus 3 over x, then we have plus 1 over x squared, then we have 1, then we have 1 over x squared, then we have 2 over x cubed. So now we're going to kind of do something that's like maybe seems a little funny, but we're going to, we're basically splitting this limit up, and there's parts of it that are going to get able to be evaluated to be 0, and then other parts that will not. And so we'll kind of be left over with some stuff that we can then evaluate the limit of. So this is going to be 0, 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 right? So we're going to be left with the limit as x approaches negative infinity of x minus 0 plus 0 over 1 minus 0 plus 0. So that means that overall we're left with the limit as x approaches negative infinity of just x. So in this case, this one's actually, I think, in some ways a little bit more obvious than some other examples we've done, because if we're trying to take the limit as x approaches negative infinity of x, well, the answer is kind of right here staring at you, right? Like if the question is what happens to x as x goes to negative infinity, well, the answer is it goes to negative infinity, right? There's not really much going on here. But that's not always going to happen for these. But what will happen is you'll be left with some kind of polynomial. So in this case, it's a very simple polynomial that's just x. But you could be left with something like x squared plus 1 or negative 2x plus 3 or something like that. But because you're left with something that's just a polynomial, you should have an idea of what the general shape of that function is. So in this case, if we were to graph the function f of x is equal to x, we know that it is a line with positive slope. And so we know that as x goes to negative infinity, so if this function is f of x is equal to x, f of x also goes to negative infinity. Whereas if you had a line that had negative slope, or if you had like a parabola or some other kind of shape, then it would have a different kind of behavior. So I would recommend going back to the video at towards the beginning of the video about limits at infinity. I went over some examples, or I kind of showed you all the different shapes that polynomials can have. And so what will happen with these kind of limits is that you'll always get down to one of those polynomials where you should just be able to like decide what the shape of it is and use that to decide what the value is of the limit. Okay, so moving on to some different types of questions. So we're going to look at number 2A was requested by a few people. So question 2A says, are the following functions continuous at x is equal to 0? Or I guess I should just say, is this function? Because we're only doing one of them. So what does it mean to be continuous? So the kind of like loose definition that we had is that a function is continuous if it has like no breaks in the graph. So no asymptotes, no like jumps, no holes, like nothing, no breaks in the graph. Like if you could draw it without lifting your pencil, then it is considered to be continuous. So the more kind of technical definition that we have that I want you to be able to use is that a function f of x in general is continuous at x is equal to a if the limit as x approaches a of the function agrees with plugging a number into the function. So in the case of a piecewise function, basically what's going to happen is if the limit exists, so if the limit as x approaches 0 in this case exists, and if that number agrees with the same thing you would get by just plugging 0 into the function, then it will be continuous. The more intuitive way of thinking about it is that basically if the two pieces of the function match up and there's no hole, then that would mean that it's continuous. But let's at least go through the motions of doing this limit definition, just because I think it's I want you to understand how this limit idea connects to something being continuous. So what is the limit as x approaches 0 of this function? Well, we would need to do the limit as x approaches 0 from the left and the limit as x approaches 0 from the right, because it's a piecewise function. So what's going to be the limit as x approaches 0 from the left? Well, because this is the function that you use when x is less than or equal to 0, we can just plug 0 into that function. Or you could draw a picture. For the sake of time, I'm not going to draw a picture for this one, but it's going to be the exact same idea, because you're basically using either the graph or the equation to see what's going on when x is equal to 0. So what is cosine of 0? Well, again, looking at the unit circle, if you go to an angle of 0, so that's here, the coordinates of this point are 1, 0. And what is cosine? It's the x coordinate of the point, and so cosine of 0 is equal to 1. And then if we are going from the right, then we're going to use now the bottom equation, because that's like the part that you would use when you have values that are above 0. So now we would plug in 0 to e to the x, and you also get 1. And so together, these tell us that the limit as x approaches 0 of f of x is equal to 1. So the limit exists. And then the other thing we would need to check is, what do you actually get if you plug 0 into your function? So in this case, if we want to plug 0 into our function, we're supposed to use the top equation, right? Because that's the equation you use when x is actually equal to 0. And so we also get 1. And so because the limit as x approaches 0 of f of x is equal to 1, or sorry, let me write this another way, is equal to the same thing that you get by plugging in 0, which is equal to 1, we say that yes, f of x is continuous at x is equal to 0. And so what could it go wrong? Because this might feel like a lot of steps for something that maybe we wouldn't have had to do all these steps for, but like, let's say that there was something, I'm just going to make a slight change in this function. If we instead had this be just cosine of x if x is less than 0, So we would get the same value for the limit because the limit doesn't care what's happening at x equals 0. It just cares about where the graph is heading. So you could still actually plug 0 into these functions, even though they're not defined at 0, it's still kind of where the graph is heading when x is equal to 0, or as x approaches 0. But then when we got to this part, then we would have to say f of 0 is undefined. And so if the limit exists, but the function value is undefined, then this part cannot be true, right? This part is only true if the limit agrees with the function. So if the function is undefined, that doesn't make any sense. Another way that we could kind of mess this up is, so let's again leave it like this, and then maybe I just throw in something else. Maybe I say f of x is equal to 2 if x is equal to 0. Well, in that case, then f of 0 would be equal to 2. And so again, they wouldn't agree. The limit would not agree with the function. So that's what even though it maybe seems like, of course, these all work out, there are situations where they won't. And by the way, if I put a question like this on the test, I'll kind of break it down into steps and actually ask you to evaluate some of these limits, just because I know we didn't do that much practice with this. And there are other ways to answer this. So if I'm looking for you to answer it with limits, I'll kind of add those questions in along the way. Okay, so let's look at, and by the way, actually, so the one where you take away, this is actually part B. So part B is not continuous because even though the limit would still equal 1, the function is not defined at 0. And what would that look like in the graph? It would mean that there would be actually just a hole at x is equal to 0. Okay, so next up we have number 3. So 3 is talking about, again, continuity. So it asks you to find all discontinuities. So by the way, in the original form of the midterm that I uploaded, I had a part where I said to determine whether the discontinuities were infinite or removable. I took that off because we didn't really focus on that. So if you were looking at an earlier version of the midterm review, you might have seen that and gotten confused about it, but that's not, I'm not going to be testing you on that. So the first function is 2x minus 4 over x cubed minus x squared minus 2x. So where is a function in general discontinuous? Well, if it's a piecewise function, you have to worry about the place where they're kind of pasted together, right? So like in this example, we had to worry about 0 being continuous or not, because that's where these two pieces of the function were pasted together. If you have a function that is not a piecewise function, then the only places it could possibly be discontinuous are going to be places where it's undefined. So we want to look at basically where is g of x undefined. So how do we do that? Well, we basically just look at where is the denominator equal to 0. So if we take the denominator, and we don't even have to worry about the numerator, let's just take the denominator and set it equal to 0, and then we can figure out what are those values, x values, that makes it 0. So we can factor out an x, right, from all of this. We're left with x squared minus x minus 2. And then we can factor this part on the inside. This factors as x, let's see, x plus 1, x minus 2. And so that tells us that there are 3 different values that could make this 0. So if you plug in 0, that's one possibility. If you plug in -1, and if you plug in +2, all of those numbers would make the denominator equal 0. So those are all going to be the discontinuities in the function. So B is a little bit different, but same exact idea. So B was h of x is equal to 1 over x minus 1 over 5 over x minus 5. So again, we want to just figure out like what numbers would make this undefined. So in this case, we have multiple fractions going on. So we have kind of two denominators to check. We have this and we have this. So we have to make sure, we have to look at what numbers make each denominator 0, because either one of those numbers would mess up this function, right? And that would mean that there's a discontinuity. So the first one, so if you are looking at 1 over x, that would mess up this first fraction right on the top. And then what number would make the second denominator equal 0? 5. So if you plugged in 5, you would be okay on the first fraction, but the second part would be messed up. And if you plugged in 0, the overall denominator would be okay, but you would have you would have something that's undefined within the fraction. And so both of those are going to be places where this function has discontinuities. Okay, so next up we have number 4. So I'm going to just pull up this graph here because number 4 is a limits problem with the graph. So basically, I'm not going to go through all of these, so maybe we can just pick one of the numbers and kind of look at that one. So maybe let's look at 2. I think 2 is a good example. So we're going to look at these 2 questions and these 2 questions. So if we're trying to find the limit as x approaches 2 from the left, that means that we are coming in from the left and we're trying to see what height is our graph approaching as x approaches 2 while staying on the left side of 2. And it looks like the graph is getting closer and closer to a height of -1. So now if we're looking at the limit as x approaches 2 on the right, we're kind of coming in on the function and we're seeing what height is the graph getting closer to as x gets closer to 2 while staying to the right of 2. And it looks like it's approaching a height of 2. So because these two don't agree with each other, that tells us that the limit as x approaches 2 overall does not exist. It's undefined because the left and the right hand limits don't agree with each other. Now, f of 2 is completely unrelated to the limits. So when you're trying to evaluate the actual function, you're not worrying about the limits. You're just looking at, if you go to an x value of 2, what is the function value at that point? So you're basically looking for what is the part of the graph that is actually kind of like filled in at 2. So if you look at this part of the graph, there's a hole. So you're not supposed to use that part of the graph when x is equal to 2. If you look at this part of the graph, you're not supposed to use that part because there's also a hole. And so the only point that actually exists at x is equal to 2 is this point up here. And so that tells us that f of 2 is equal to 3. And so this is an example of where this function is not continuous at 2, right? Because the limit doesn't even exist, and then the function is a different value than any of parts of the limit, so it's definitely not continuous. Then other parts of this are similar to that part. Okay, so let's move on to, let's see, so let me just look at what this next one is. Okay, so let's do 5a. So 5a was one of the limit definition of the derivative. So we're going to use the limit definition of the derivative to find the derivative of the square root of x plus 4. And then we are going to, we're going to also see what the slope of the tangent line is at 2, and then we're going to determine whether the original function is increasing or decreasing at x is equal to 2. So the limit definition of the derivative is the limit as h approaches 0 of f of x plus h minus f of x over h. So as I've mentioned a few times in videos, you do need to know how to use this definition. On all other questions on the test, you don't need to use the limit definition. So later on, we'll do some examples of just taking the derivative with derivative rules. You can assume that you're allowed to use derivative rules unless the question specifically says use the limit definition. All right, so what is that going to look like for this function? It's going to be the square root of x plus h plus 4 minus the square root of x plus 4, all divided by h. So this is actually pretty similar to one that we did earlier, where we just have to multiply by the conjugate, right? So we're going to multiply by x plus h plus 4 minus the square root of x plus 4. And we're going to do the same thing in the denominator. So what's that going to look like? Well, in the numerator, the square roots are going to go away. So we're going to be left with x plus h plus 4. And then remember, we have to do this thing with the parentheses because we're going to take x plus 4 and we're going to subtract that whole thing away. And then in the denominator, we leave all this stuff here. We don't distribute anything because that will just make it harder to see what can be canceled out. Okay, so what happens in the numerator? Well, we have an x and we have a negative x. And so there's not going to be any x's left. We have a 4. Maybe let me circle what I'm talking about. So here, right, we have x and then we have negative x. And then we have a 4 and we have a negative 4. So there's not going to be any 4's left. And so all we're actually going to be left with in the numerator is h. And so we're going to have the limit as h approaches 0 of just h divided by h times all this stuff. Oops, I wrote the wrong order here. So x plus h plus 4 minus the square root of x plus 4. So now we can cancel out these h's, and this will enable us to actually plug in 0. So we have the limit as h approaches 0 of 1 over the square root of x plus h plus 4 minus the square root of, and actually, sorry, I made a mistake way back in the beginning, I just realized, so sorry about that. So way back at the beginning, this should have been a plus, right? So the original function was minus, so the conjugate should have had a plus. Sorry about that. Okay, so now we can actually plug in 0 for h. So we'll have 1 over square root of x plus 4, because that we just plug in 0 for the h, and then we have another square root of x plus 4. And so altogether, that's 1 over 2 square root of x plus 4. So that is our derivative. Our derivative is f prime of x is equal to 1 over 2 times the square root of x plus 4. So now if we want to find the slope of the tangent line at x is equal to 2, we can just plug 2 in, and you don't need to go back and use the limit definition again. Now we can just plug directly into the derivative that we have. So f prime of 2 is going to be 1 over 2 times the square root of 6. And that is a positive number. So this is a positive number. And that tells us that f of x is increasing at x is equal to 2. So that answers the second part of the question. All right, so next up we're going to look at some parts of number 6. So number 6 is asking you to use derivative rules. So we're going to do, let's see, 6D and E. So 6D is the function k of x is equal to 2 over x to the 4th minus 1 over the cube root of x plus x squared over square root of x. So the first step before taking the derivative, and by the way, so you could, if you really wanted to, use the quotient rule on each of these individual parts. I think that would be definitely the hardest way to do this question. And there are going to be no questions on the midterm that require you to use the quotient rule. So you should always be thinking about how can I simplify this in order to avoid having to use the quotient rule. So in this case, we want to start by rewriting it. So again, be really careful that you don't blend together the step where you're rewriting it and the step where you're taking the derivative. I think that's the easiest way to make a mistake. So make sure that you're first rewriting it, then you're taking the derivative. You're not kind of doing them both at the same time. That's just a really easy way to run into trouble. So how can we rewrite this first part? Well, if we're dividing by x to the fourth, that's the same thing as 2x to the negative 4. And then this next part, we have 1 over the cube root of x. So cube root of x would be x to the 1/3. So this is going to be x to the negative 1/3. And then this last part, well, this is x squared over x to the 1/2. And so we can simplify that using exponent rules. So we have 2x to the negative 4 minus x to the 1/3. And then this part we have 2 minus 1/2. So that's going to be 1.5, right? If you have 2 and you subtract out a half, you'll be left with 1.5, which is 3/2. So now that we're done rewriting it, now we can take the derivative. So remember, differentiate is the verb for taking the derivative. So now we can just use the power rule. So for the first one, we're going to take 2 and we'll multiply that with negative 4 times x to the negative 5. Then we're going to bring down the 1/3, and we have x to the negative 2/3, right? If we have to have 1/3 and we take away 1, we're left with negative 2/3. And then this last part, we're going to bring down the 3/2, and then we have 3/2 minus 1 is going to give us 1/2. And so now we can rewrite this. So this is going to be negative 8 x to the negative 5, and then we have minus 1/3 x to the negative 2/3 plus 3/2 x to the 1/2. So I will specify on the exam what kind of format I'm looking for your answer. So if I don't specify anything, this is fine to leave as your answer. If I do specify that I want you to write it without fractional or negative exponents, then you're just kind of putting it back into the same format you started with. So here we have x to the negative 5, so that means it's going to be over x to the 5th. Here, so this one's a little trickier. So we have negative 2/3. So first of all, that 3 is going to be on the bottom, right, with the x. And then negative 2/3, so that's going to be the cube root of x squared. Because this number tells you, or not the negative part, but the 2 tells you the power and the denominator tells you the root. And then this last part is going to be 3 times the square root of x divided by 2. So either one of these two answers, let's say, are okay. And if I expect one or the other, I will specify on the exam. So what is the advantage of the first method? Well, on number 7, I ask you to take the second derivative. And so if you were taking the second derivative, you would want it to be in this form, right? Because that would let you use the power rule. Okay, so let's look at E. So part E is L of x is equal to negative pi plus e cubed. So I thought it was interesting. A lot of people requested this one. This is actually probably the easiest one in the whole list of derivatives. So why is this easy, even though it kind of looks funny? Well, what is pi? Pi is a number, right? It's approximately equal to 3.14. What is e cubed? Well, it's the number e, which is about 2.72, and then you take that number and cube it. So notice our input variable is x, right? And are there any x's on this side of the equation? No. So this is a constant function. So this is, pi, negative pi is a number. E cubed is a number. And so that tells us that L of x is a constant function. It's a function that is just a horizontal line at a height which happens to be the height of negative pi plus e cubed. And you could type that into a calculator and see a decimal approximation of what number that is if you're curious. But for our purposes, all we have to know is that it's a number. So what is the derivative of a constant function? It's just 0. So I just realized that I didn't answer part of the question for the other one. So the question also asks you to find the slope of the tangent line at x is equal to 1 and asks you whether the original function is increasing or decreasing. So for this one, you would plug in 1 and see what you get. And basically, if it's positive, it's increasing. If it's negative, it's decreasing. For this one, what happens if you try to plug in 1? Well, when you have a function L of x is equal to 0, that means that no matter what number you plug in for x, you always get 0. Because if you think about it, our original function is a horizontal line, so the slope is 0 everywhere. It doesn't matter what x value you're looking at. The slope is just always 0. And so that tells us that the derivative is 0 when x is equal to 1. And so that tells us that the function is neither increasing nor decreasing at x is equal to 1. So again, just be aware that when you see e, make sure that it's e to the x. If you think you have to take the derivative, it should have an x in it. If there's no x or whatever the variable is in that question, then it's not a function of x. It's just a constant number. Okay, so last one that I'm going to go over is number 10. Maybe I think I have another page left. Yeah, so let's do a new page. So number 10 is a word problem, and it says, a toddler is playing with a toy car, moving it back and forth on the floor in a straight line. So the position of the toy car after t minutes is s of t is equal to t cubed minus 3t. And that is measured in meters. So the units are meters for the distances and minutes for the time. So the first part of the question is asking us to find the average velocity from t is equal to 0 to t is equal to 2. So what is average velocity? Average velocity is the same thing as average rate of change, right? So for example, I gave an example way at the beginning of the quarter of if you're going on a car ride and you have some, your time or your speed is varying over the trip. But if you kind of look at what's your starting time and what's your finish time and how far did you travel, that will tell you your average speed over the trip, right? Or your average velocity. And so average rate of change in the case of a position function is the same thing as average velocity. So how do you find the average rate of change between two t values in this case? You plug them into the function and find basically the slope of the secant line. So we're going to do s of 2 minus s of 0 divided by 2 minus 0. So if we plug in 2 to our function, we'll get 8. So 2 cubed is 8 minus 3 times 2, so that's 6, so that's 2. And then if we plug in 0, we actually get 0 as well. So just kind of a coincidence. So we're going to end up with 2 over 2, which is 1. And what are the units? They are meters per minute. So that is the average velocity. That's if you see, overall, how far did it travel in the first 2 seconds? Or maybe not even how far it traveled. What's its position? What's the change in position from 0 to 2? Because it might have gone forward and backward during that time period. And then how much time has passed? 2. And so dividing those, you end up with the average velocity. Okay, so let's do part B. So part B asks you to find the velocity and acceleration functions. So I want to just kind of differentiate what's going on here. So when we're talking about average velocity, that's average rate of change, right? That's the slope of a secant line. You're kind of looking at 2 points on the graph and you're finding the slope between those 2 points. It's not telling you what's happening at any specific moment. It's just telling you the average trend. When we find the velocity function, that's going to be the function that tells you the instantaneous velocity at any moment. So it's different. The instantaneous velocity is like when you're driving, if you look at the speedometer and what is it saying at every specific moment. Whereas average velocity is like overall on the trip, what was your average speed? So how do we find the velocity function? Well, the velocity function is going to be the first derivative of the position function. So our position function was t cubed minus 3t. So that's going to be 3t squared minus 3. So, and then why is that? Why is it the first derivative? It's basically because velocity is a change in position, right? You're looking at like how fast are you going means, as time goes on, how much ground are you covering? So you're looking at the rate of change of the position. So how do we find the acceleration function? Well, acceleration is about speeding up and slowing down. So speeding up and slowing down is talking about how is your speed changing, right? So that is going to be the rate of change of the velocity. So it's the derivative of velocity. So in this case, that gives us 6t, and that's it, because the derivative of that is 0. Okay, so now we have our velocity and acceleration functions. So the next part is to find the velocity of the car after 1 minute. And then I also ask you to include units and explain what it means in the context of the problem. So if we were to find the velocity after 1 minute, that means we need to plug it into our velocity function. So our velocity function is right here. So we're going to do 3 times 1 minus 3, and that gives us 0. So what are the units in this case? Well, we said earlier that the position units were meters and the time units were minutes. So think about when you're talking about think about miles per hour, right? When you're doing a speed or velocity, your units are going to be distance over time. So that is the velocity. So what does this mean in the context of the problem? Well, it means that the car is momentarily not moving forward or backward. So this means that the car is not moving forward or backward at t is equal to 1 minute. So practically, what does that mean? That, well, in this case, it would mean probably that the toddler is in between, they maybe push the car forward and they're pausing for a moment before the car starts to be pushed backwards. So it's kind of this in between Like when the velocity is 0, it tends to be because it's a transition period before or between moving forward and backward. So the last question is to find the acceleration after 2 minutes. So that means that and I guess I should write that out. So the acceleration after 2 minutes. So that would mean that we're plugging 2 into our acceleration function. So remember, our acceleration function was 6 times t. So we're going to do 6 times 2, which is 12. And so what are the units? Well, we talked about this in the video I made, but basically it's like you're taking meters per minute. So that would be velocity units. And then you're dividing that by minutes again, right? Because you're saying like, so whenever you have a denominator like this, you're kind of saying, you're talking about how this unit is changing as this unit progresses. Miles per hour, how far is a car traveled as time goes on. And so if you're talking about acceleration, now you're talking about how quickly has the velocity changed as time has gone on. So you're doing meters per minute per minute. But there's a nicer way of writing that, which is that we just write it as meters per minute squared. So we're just kind of putting the square there to represent the fact that we've divided by minutes twice. And by the way, so if I were to ask, what does this tell you about whether the car is speeding up or slowing down, you currently don't have enough information to answer that. So how would you figure out whether the car is speeding up or slowing down? You would have to also find the velocity after 2 minutes. And we talked about in the video about acceleration and velocity, how something is speeding up when its acceleration and its velocity are in the same direction. So in this case, because the acceleration is positive, the velocity would also need to be positive. If the velocity after 2 minutes was negative, that would mean that the acceleration is not pushing in the same direction as the car is moving, and therefore it's actually slowing down. So, I didn't ask you for that, but I just wanted to briefly mention it. All right, so that is it. If you have more questions from the review, feel free to send me an email, and good luck with your studying.